Olá, voltamos com a segunda parte do módulo Rádio Digital DAB, Tecnologia e Status de Mercado, que será apresentada pelo Dr. Sabel. Ele irá comentar, inclusive, a capacidade do DAB de funcionar no modo rádio híbrido. Les, please.
Hi, I'm Les Sabel, and I'll be presenting DAB Plus Digital Broadcast Radio, the technical basis today. We'll run over DAB features. We'll talk about the head-end system, the transmission system, and hybrid radio. So the basic features of DAB Plus. Well, the first thing to know is that DAB Plus is delivered with multiple audio services per ensemble, or you might say per radio frequency transmission. Now, of those 18 to 24 DAB audio services, each audio service can have its own bitrate adjusted to provide the appropriate quality for the content that is delivered. And each radio service or station, you might say, has its own program associated data. We also have some advanced features. We have data services, and we can deliver video as well. So mobile video is also possible through DAB. So the first thing is stations. Being spectrally efficient design, DAB provides a room for a lot more services. So here we see a picture of Australian commercial radio before DAB. And now we see what it looks like with DAB. So before, in Sydney, for example, there were about 20 services, total services in AM and FM. Now there are over 60, so 3 times as many services. And this is a critical point to be able to compete in a ever-increasing media environment, particularly when there are a number of digital giants trying to stream radio, such as Apple Radio, Spotify, Google, and so forth. So we see some examples here in the UK. Heart added an extra station called Heart Extra. In Norway, NRK P1, their main service, had a P1 Plus. And the BBC in the UK basically doubled its number of services. DAB Plus also offers the flexibility to add pop-up stations. And they are stations that are added for a limited period of time. And they usually use existing bitrate from other services. So for example, we might have ELF at Christmas time, or we might have a live Olympics station during the Olympic Games. Looking at those basic features again, most importantly, we have station lists, we have names. We don't have to remember numbers and frequencies. And those names can be accompanied by logos. So very good for brand recognition. We have dynamic label text, which will deliver information such as the song's now playing, next playing, weather, news, information such as that. And we have slideshow images as well, which are often on music stations containing album art. But it could also be the talent that's presenting the program, or it could be weather or news, whatever the broadcaster wants, really, within the limits of the legal requirements. We have data services. Now, the main data services are traffic information through the TPEG system, which provides all the normal congestion information, it provides parking information, fuel prices, and so forth. We have the journal line hierarchical categorized text system, which is typically used for sports and news and weather. And if you wish, you can even have custom applications. The advanced features include service and program information. So that's the station and service logos, website links, program schedules, and a number of other things. And announcements, that's what's used for traffic, where you can vector your current station to a traffic station for example, say 5 minutes to give you the traffic flash information. And that's also used for emergency warnings. Importantly, traffic announcements in general are controlled by the receiver and by the listener, except for emergency warnings where all controls are overridden. So that's for very, very important emergency warnings. And we also do service following, where you can set the receiver to remain on the same station even when you move between areas on different frequencies. So let's look at the actual system itself. So the system is divided basically into two parts. There is the head-end part, which has the encoding and multiplexing, and we have the transmission part, which does the modulation and coding. And in between that is what's called the Eti interface. So we see here an example where audio sources from a number of different types, from analog to state-of-the-art audio over IP, that uses AAC Plus or HEAAC version 2 and has additional Reed-Solomon encoding for additional protection. With our program associated data, and very importantly, that program associated data is also protected by the Reed-Solomon encoding, making it more robust. And of course, the data services. And all of those are delivered to the multiplexer part of the system. Now, to allow the receiver to decode the delivered information, we need to have multiplex configuration information so that the receiver knows what bits are in what part of the transmission signal. We have service information, so that's things like the label of the service, the language, date and time, and those service linking announcements, and of course the service and program information as well. And all of that is delivered under the control of the system settings, where each service or station has its own forward error correction options, its own subchannel bit rate, and its own audio coding options, all delivered to the multiplexer. And the output is the ETI stream I talked about before, which is these days, of course, encapsulated in an IP form, and we call that EDI. The construction of these systems, just 10 years ago, it would be all separate boxes. We have different boxes for audio encoders, for multiplexers, for pad servers, controllers. These days, it's all done on server platforms, and typically we'd have two server platforms, one for the main and one for a redundant spare, all operating as hot standby. And within those servers, we'd use virtual machines. And here's an example how we might include the encoders on a virtual machine 1 on server 1 and its redundant alternative on server 2. Same with the multiplexer in virtual machine 2. We might use virtual machine 3 for the pad server and the multiplex controller, and maybe have an additional virtual machine for network management. Now, the overall structure is typically a star type of situation where we go from the audio encoders through a main studio, through a distribution cloud to a number of transmitters. It could be one, it could be many. These days, what we see now is that the encoding and multiplexing is actually provided through servers in a system in the local cloud, or if economic and advantageous, it could actually be done in the public cloud as well. And we have an example here in Australia where that is being done for some broadcasters. They've moved all of their hardware into a data center in the cloud, and it's all run remotely. And that offloads all of the maintenance and monitoring and engineering required to the data center. The downside is you have to make sure you have enough transmission capacity through the cloud at the time. Okay, let's turn to the transmission system. So all the modulation and coding is actually done in the transmitter exciter, in the transmitter itself, from the instructions delivered over ETI or the EDI stream. It uses DQPSK modulation for robustness and a concatenated code. As I mentioned before, we have an inner code, which is the Reed-Solomon code, and an outer code, which is convolutional code. Now, typically that code, the outer code, will be a rate half code and deliver 1152 kilobits per second per ensemble. But it is flexible. You can have stronger coding and have less capacity, or weaker coding and have more capacity. And of course, DAB was the first transmission system to use OFDM. It was before 4G, it was before DVB-T. It's using the same basic technology that even 5G was used, so it's well ahead of its time. And using OFDM means it will support single frequency network operation. And typically we have a guard interval of 246 microseconds, which provides a minimum of 73.8 kilometers per cell. We operate in transmission band VHF band 3, and there's 32 available frequency blocks within that band. In some countries, they have additional services in 13A and 13F, but they're often not available due to use by others. And we use a reference arrangement of 18 services per ensemble at 64 kilobits. Now, importantly, we have a requirement for a critical mask filter, and that is used to ensure that we have very, very small guard bands between adjacent channels. And typically here in Australia, for example, in capital cities, we will use channels 9A, B, and C right next to each other with no problem at all. Usual transmission chain where we've got multiple ensembles, shown as channels here, going through a combining system, some sort of patch panel, to a transmission tower. And we see some examples here of a normal transmission tower and one with a radome for extreme weather conditions. An example of coverage, here is Sydney. We have a main transmission site at a site called Artarmon, 45 kilowatts, pardon, at 196 meters above ground level, and that gives us about 30 kilometers at good urban indoor grade coverage. The road coverage will extend further. That goes to almost 40 to 50 kilometers. Now, Sydney is a big area. As we can see here, that's 30 kilometers. So to fill that area to the west of the main city, which is just south of the Artarmon site, we need some additional transmitters. So here we see some additional repeaters, and we have 2 link-fed repeaters in the west, Wimberley and Bergeley, and 3 on-channel repeaters along the coast and in the city to give extra coverage in areas which are shadowed. So let's turn now to hybrid radio. And hybrid radio is the next step in the evolution of radio. It combines IP and broadcast. So we use broadcast for the main transmission because it gets to everybody as a one-to-many transmission system, of course. So it's very cost effective. And then we use broadband to provide additional extensive features, including logos and program information, interactivity, other metrics, analytics, alternative content, and the list is increasing as we go. Now, this sort of service is already available in a range of cars, including Audi, VW, Porsche, and BMW, and is being developed for most brands around the world as we speak. So, in summary, I'd just like to say the DAB digital radio provides a wide range of advantages over traditional analog radio. It's spectrally efficient to allow significantly more services to be provided in an area. And typically we target dense urban areas near the main cities to town type levels of maybe a few thousand people. Really, it's anywhere where you're going to use or provide more than about 9 or 10 services. It is the most cost-effective radio delivery system. It's robust with high audio quality. We have text and images, a range of advanced features, hybrid capabilities, and important, we have a very wide range of receivers for both domestic and automotive cases, with the recent number from the middle of this year, over 93 million installed receivers around the world. And importantly, it's all through open standards defined by ETSI. And we can see there the main standard, ETSI EN 300-401. If you want any more information about this, please contact WorldDAB or myself. And with that, I'll say thank you very much for your attention. Thank you very much for the opportunity.
Esta é a trilha 7 Rádio do 7 Experience Academy. Obrigado.